Okay, go ahead.
All right.
Great. Hello, everybody. Thanks for joining us for the Pathway presentation today. You're going to hear from a couple of our faculty members. But first is going to be from Professor Christian Arens, who's a key member of our new quantum engineering area for electrical engineering students. So he's here today and has some slides up ready. So thanks for being here, and you can start when you're ready, Professor Arens. Thanks.
Sure. Thank you so much. Well, thank you, Sharon, and thank you for everyone who honors us this. I think it's a great pleasure actually to present the new Pathway program in quantum engineering. And let me tell you first of all who I am. So my name is Christian. I joined, I think, the faculty in ECE in 2022, and my lab is called the Quantum Control and Quantum Information Lab. So later on, when the slides are uploaded, this is actually a link, so you can click on that and learn more what I'm actually doing. Roughly, my background is actually quantum computing and quantum control theory. So roughly, I try to make quantum computers better. So it's right now, it's actually an exciting time because we're living in a time where we see that more and more the stuff we do here as faculty and academia transitions more into actual technologies company aim to use. And what you see here in the background is actually an atom with the world in the middle. And roughly speaking, what quantum technology is, we try to leverage the strange effects of the small quantum world to make new technologies out of that. And I think you might have heard about quantum technologies already, and I think the media picked up on that too. So for example, what you see here is an article by the New York Times, which appeared in 2019, and they reported on a very famous experiment done by Google. And so they built actually a quantum machine, and they showed that that quantum machine can have a huge computing advantage over the best known classical computers. So what I mean by that is when you read it carefully, they say, okay, so the Google quantum computer took 3 minutes and 20 seconds to solve a problem, a certain computational problem, whereas the best known classical computer, or the best known supercomputer, would take 10,000 years. And of course, that sounds very, very impressive. And I was really excited when I saw that. Unfortunately, IBM, the rival company, right, came up the next day and said, no, we can actually do it in 3 days with the classic computer. Nevertheless, this is a huge milestone that made it actually into the New York Times. In general, like quantum appears all over the news. For example, the Washington Post in 2020 titled "Feds Put Cybersecurity for AI and Quantum Computing in the Spotlight" because they realized that quantum computing is actually a threat to national security, because you can crack actually the best known encryption protocols. And Congress realized that too. So in 2018, the so-called Quantum Science Act, or actually the Quantum Computing Act, was basically signed by Congress. And what that actually means is that the US government provides loads of funding for exploring and developing quantum technology. So when I say quantum technology, we often forget that we actually have quantum technology. So what I took here is just a little cutout from the website of the government that tries to fund quantum technologies. But I emphasize that we actually have already known technologies like magnetic resonance and other things for medical imaging. So in the end, you have little quantum stuff in your body, right? And what you actually do if you go into that tube, a magnetic field is turned on and they flip the little quantum particles in your body. It sounds a little scary, I know, but what they do is they flip these things and they record the magnetic field that is emitted from that. But what I actually mean with new quantum technologies is this. It actually holds a much greater promise, and I often call that the second quantum revolution. You can actually use quantum effects that happen at the very, very small scale to speed up computing, to do networking, and to do sensing more carefully. So what I mean by that is the new emerging technologies. I guess the most famous one is quantum computing, right? So on the left, you see actually a quantum computer here from Google. And the goal is really to speed up certain computations classical computers are capable of. But at the same time, you can also use quantum effects to communicate with each other. For example, you can imagine like having nodes around the world, and then you use quantum computers at each node, or just little quantum systems that talk to each other. And you can imagine like a quantum internet that is created in this way. At the same time, you can build better sensors. So what you see here is a schematic representation of a so-called quantum sensors. And what you can actually show if you use like little particles like that to sense, say, the surface of this material, you can actually show that you get an enhanced precision. And the interesting thing for me personally is, even though I'm a trained physicist or an applied mathematician, actually, this technology is quite multidisciplinary. So in the end, to understand, to study these technologies, these new technologies, to make them better, you need to combine tools from physics, math, computer science, and engineering, which I personally find very challenging, of course, because to bring all these people together. But at the same time, it's a huge advantage here, right? Because it's the first time that several people from different fields come together to make these new technologies. Bottom line message here, it's multidisciplinary. So we need to learn and train the future workforce in all these different aspects. So the goal of this pathway program is really to prepare you, the future scientists and engineers, to use these technologies and improve them. And as I said, that is very multidisciplinary in the sense that you need to know something about physics, math, computer science, and engineering. So how did this pathway program look like we created? Well, so the structure is as follows. So first of all, we're still creating it, right? We're actually in the process of creating new classes. So I kicked it off this time with the pathway class, which we called Quantum Mechanics for Quantum Information Science. So I'm teaching that actually right now, and it will be offered basically every semester. And it's the starting point of establishing basically the language we need to formulate or to describe quantum technologies and learn about it. And that language, naturally, is the language of quantum mechanics. And you may then wonder, okay, what is the difference to this quantum mechanics class than any other quantum class in physics, for example? Well, here we really target applications in quantum information science, and we establish the tools and language that are needed, and don't use the tools that are not needed, right, that are traditionally taught in quantum mechanics. So if you have taken that class, basically establishing the language and the foundations of it, well, you can then go on in the technical elective to specialize it. So what we're going to offer in the spring is a class called Quantum Mechanics for Engineers, and that is the class taught by Professor Michael Gorel. And what he's aiming to do is in revising that class a bit and focusing more on the experimental implementations of these quantum technologies. I, on the other hand, will teach a class that is about quantum computing, where I really focus on computing all the language, all the math, all the tools, which you can apply then here. Whereas this class is basically more applied. You really learn about the technology itself, how you build these things. Whereas here, I will establish the theoretical foundation for quantum computing. Basically, why is quantum computing expected to be much faster for certain problems than classical computing? That is the direct threat while I'm teaching this class. But then we go on, and this is so far tentative because we're still planning on adding these additional classes to the pathway. Is, for example, my background is in quantum control theory. And I would love to teach or create a class in quantum control, combining it with the expertise you bring already in from control engineering. So roughly speaking, what you could think of as a quantum system or quantum computer is a complex system with control inputs and outputs. And the outputs are basically the solutions to the computations we want to do, right? So the task is then to find the control inputs to make this complex system more robust, more effective, faster. So basically, you can leverage and apply all the tools you learned already from control engineering to control quantum systems. Another very interesting aspect, another interesting part is, in the end, how do you control a quantum computer? Well, you shine a light or lasers or magnetic fields, or in general, electromagnetic fields. An interaction of an electromagnetic field with matter is basically studied within quantum optics. So Professor Sina, who's another colleague of mine who created the pathway, teaches right now quantum optics, and we try to offer that course in the future too. However, we also try to implement and create a class called open quantum systems, because in the end, the main enemy of quantum computing is noise. So the reason why we don't have a fully functioning quantum computer yet is that noise washes out the quantum effects we want to leverage to see a speed up. And a system that is noisy, we call open quantum system. Open quantum system in the sense that we have a system that interacts with all its surroundings, that causes noise, and that noise destroys the system, basically. So in order to study it and in order to prevent that happen, we need to study open quantum systems to deal with the noise. And in the end, well, we finally want to build these things, right? So I hope that there will be another class that offers more details on how you actually model a quantum device, which physical effects play a role, which wires go into that, what are the control things you need to play around. All right, so this is basically roughly the idea. So far, we are here and we aim to establish this. And then you may wonder, well, so what's the point of it besides curiosity, right? Well, there is a huge growing job market in quantum computing and quantum technology in general. So when I started as an undergrad, there was not a single company doing quantum technology. Now you have several established companies like IBM and Google and Amazon, but we have more and more startups popping up. And I want to emphasize that also banks like JP Morgan or HSBC, which is the British bank, they hire quantum engineers because they need people to advise them what to invest in, right? Can quantum computing enhance finance or predicting stuff at Wall Street? That's why also banks are really interested in it. So it's not just the traditional, okay, we do physics and quantum computing stuff. No, we need quantum engineers that go into banks and tell basically the bankers whether it is a technology to invest in, to distinguish the hype from the actual need. And I, out of curiosity, because there are so many startups, and it's not even close to a complete list. I was actually Googling how many startups do exist, right, in quantum or companies. And here's a plot I got. So on the x-axis is number of years, y-axis is how many companies or startups are established as year. And as you can see, there was a huge exponential increase at the time of 2013, 2014, 2015. And well, I guess we all know what happened here, right? When it goes down again, I guess the pandemic hit. What I'm trying to say is, even though I could not list all the companies that do quantum technology or that invest in that in this chart, this plot shows nicely that there is an exponential growth. I mean, again, stopped by the pandemic, I assume, for quantum jobs. But it's not just companies. Also, national labs have heavily invested in quantum computing and have many researchers that focus on quantum computing, because obviously it is it's a threat of national security. Because if you can crack the best known codes, well, nothing is secure in that. I don't want to scare you. We're really good scientists working on that, right? To try to prevent that happen. But that's why national labs are very much interested in it. But last and not least is, of course, also the faculty, right? Also academia, because we need professors, we need teachers, we need labs assistant postdocs who actually do the research and teach these things. All right, so overall, what I just want to emphasize here, it is a great time to get into quantum technology or quantum computing, because it is the first time that we actually see that this purely academic field that started, say, in the 80s or 90s, transitioned into something we actually built, right? With the hope that it will change basically the future of the human race. That has such huge potential that I believe in. All right, with this, I want to stop here and leave it open for questions. If you have any questions, feel free to reach out to me anytime. I'm most of the time here. Basically, I live here. So also stop by my office if you're interested in quantum computing or quantum technology, or if you just want to chat. All right, well, with this, I want to thank you, and I open the session for questions.
Thank you, Professor Ahrens. We did have a couple of questions, and students, yes, this is a brand new area, and it is just being offered in brand new courses on the Tempe campus now. It's not quite there online yet, and we don't have a due date on the online delivery of these courses just yet, but thanks for asking. Christian, any thoughts on that from your end?
It's actually a good question, because I'm thinking myself in creating hybrid classes, because obviously you can use technology like iPads, right, and animations to teach this class online. However, in terms of a timeline here, I don't have one yet. So I would like to do it as soon as possible, but I would say first we would establish the core courses of the Pathway program, run it once or twice, like one cycle. And I think then the next step is to create actually hybrid versions of these classes. So rough timeline, maybe 1 to 2 years-ish.
Yeah, thanks. Yeah, I know a lot of students, online students, might miss this exciting new area, but we still like to talk about it. So even the discussion of it hopefully gets your minds turning for sure. And then we had a question about instructors for spring, and we have a new instructor who will be joining us for spring, and we're just finalizing that. So David, I don't have an exact person just yet, but thanks for asking that. Let's see. This is an interesting question for you, Professor Ahrens. Are there any rumblings about potential applications of quantum engineering to the energy sector?
Oh yeah. Oh man, that's sorry for. I mean, yes, absolutely. So there are many. I mean, it depends on what you mean by energy sector because it is quite a broad field. But of course, so for example, the national labs, they invest heavily into that. For example, to study fusion better, to simulate the processes, that's what's going on when you do fusion, but also nuclear reactions, right? In general, you may wonder, well, how can we be more energy efficient? And in the end, those are problems we try to simulate and try to make better, right? And at some point, we can't really do that on classical computers anymore because the models we have, a classical computer can't really solve them for large systems. So that's where quantum computers can be really useful. And I know for sure that especially within the national labs, energy is a big focus for quantum computing. And in academia, I think more people go into that. Regarding startups and companies, I don't know of any, to be honest. However, it is certainly a big application of quantum computing. Yes.
Thank you. And I missed one. Sorry, Ivan. I saw your question at the top there just now. So Ivan is asking about how does quantum computing user interface work? Is it the same as Windows, Linux, etc., or is there some new interface?
That's an excellent question. So of course, when I say quantum computing, and I haven't really talked about what quantum computing is, so that's why really we need this pathway. That's why we thought it's a good idea to have a pathway course or a pathway program on that. Because of course, you imagine it's something like Windows or Linux or OS X, right? That you sit in front of your computer and you play around with your mouse, I assume, right? And that's the hardware you're using is just quantum. Well, it is basically not like that at this point. So at this point, we're really at the beginning. So think about like, we're not even at the transistor stage when you compare it to classical computing. So big question is, what is actually the interface to program quantum computers, to write software for it? And that is a question that is not answered yet. So for the IBM devices ASU has access to, there's a very famous software package called, or it's a toolbox actually called Qiskit, Qiskit, and it's offered from IBM and developed by IBM to access actually quantum computers. It's Python based, but it's not like a track. I mean, some things are track and drop, but it's not that you really have an operating system yet for quantum computer. And the reason for that is basically that there are only a few handful problems known where quantum computer is actually much better. In fact, there are many other problems known where quantum computer is actually worse than a classical computer. However, some killer applications regarding computing, other very important problems, quantum computers it can be proven that quantum computers are better. So it is better to compare, I think, with supercomputers. So you would not run a computer game on a supercomputer, right? You're not playing Fortnite on the cluster of ASU, right? You submit jobs like weather forecasts, whatever, to supercomputers, let them run and retrieve the data. And in a similar fashion, quantum computers can be considered. Long story short, they're useful for a handful of problems, like very useful, but we don't really have an operating system yet, or we don't even know what it might look like to program quantum computers. So in the near future, I'm not envisioning that we will have a desktop computer that is a quantum computer. I'm envisioning it more like a cluster where we submit jobs to. That being said, though, there's a quote which is very famous by the developer, the inventor of IBM, who said, a classic computer, and that was, I don't know, in the 80s, I guess, a classic computer, we don't really have an application for it. Maybe just a handful of people worldwide know what to do with it, right? And I would make the same statement for quantum computing, roughly. But well, now we're sitting here, and I guess everyone is in front of a computer, and we have iPhones and all that kind of stuff. So who knows what the future brings?
Thank you. That was a great question. That's and then I think we have a couple more in here. Students adding a link to how to install Qiskit on his computer, but he says it's difficult to get into. So he says it's easy to get into, gets easy to get started, but difficult to get into it. So
yeah, let me add to that. The class I'm teaching right now, the pathway class, it has a lab component, and the lab component is Qiskit. So lab 0, so the first lab, the first lab was really installing Qiskit and playing around with it. And then you go on basically in that class to do simple stuff, right? And that becomes more and more complex the more deeper you get into the material. But the idea is really to use this hands-on approach to learn the fundamentals of quantum by actually using IBM devices at the same time, and at the same time learning the theory behind.
Great. I think I have another question here about from Umair, as he's asking if quantum computers need amplification and switching.
Yes, absolutely. That's a very good question too. One part of my research is actually about amplification. And you can think of classical amplifiers, right? Who amplify your signal. What is the main metric of a classical amplifier? How good is it? Well, it's the signal to noise ratio, right? You don't want to add more noise when you amplify. And when it comes to quantum, so these things are very sensitive and very small. Of course, you want to amplify your signal that comes out of the quantum computer, but you do it in a way, you want to do it in a way that you don't add more noise. So what you actually want to do, you want to do it at the level where you add the smallest possible noise components possible, which is in itself quantum. So we call it then a quantum amplifier, which is limited only by the laws of quantum mechanics. So yeah, it's really important task. So basically maybe I can go back for a second. Maybe you see that even here. So you see all the wires that go into the quantum computer. These wires are used for control and readout, and the signals in the form of, say, microwave fields that come out there are actually amplified through quantum amplifiers. And it's a huge area of research to make these quantum amplifiers actually better.
Great, thanks. And just a couple of quick follow-ups before we wrap up here. Let's see. Ivan from he was wondering if the interface would be like a Neuralink style interface.
Not 100% sure what you mean by the Neuralink style.
Yeah, let's see if he has a minute to clarify that. And then finally, there's a new question here that
maybe just a second. When you say Neuralink, you don't mean with your brain, right? That you access the quantum computer just by your mind. Please clarify. Anyway.
Yeah, he's saying yes.
Really? Okay. Well,
that would be exciting.
That would be interesting. That's a little bit creepy, to be honest. But I recently read that Elon Musk wants to put a chip into somebody's head to access a computer or something. To be honest, I don't know much about that. But the technology in itself is not mature yet, right? It's really in the early stages. Think of computers in the 70s and the 80s. That's pretty much where we are. So talking about the connection with your brain, well, that's if that happens, and it could happen, right? Why not? That is, I think, far in the future.
I think this would be. I have a final question here. I know there's some follow-ups, but we just have a couple minutes here. But the final question I think would be a great one to end on was an anonymous user here is asking why EE is a good fit for the quantum engineering discipline at ASU. Is it because EE is best suited to deal with necessary math and abstract thinking?
That is an excellent question, and it's a perfect question to finish, because I myself am not an engineer, right? I'm a trained physicist / applied mathematician. And I'm actually really glad that I ended up in the engineering department, because in the end, what we're actually facing are engineering problems. It has transitions out of these fundamental problems that we study in physics to something practically applied, right? And engineering, as you probably even know better than me, combines many, many disciplines. Again, math, physics, computer science, these things come all together in engineering. And in the end, what do we have, right? We have a complex machine, and we want to make that machine better. So, for example, classical control theory was born due to the needs of the Industrial Revolution, right? You had steam machines, and you wanted to make that efficiency, these steam machines better, the efficiency of that. And that's how control theory was born. And in the end, well, it was really successful. In the end, we were able to land on Mars, right? With basically the basics of control theory. And in a similar fashion, we can think of a quantum computer as a complex system that you try to make better, like in terms of noise, in terms of efficiency, in terms of many, many things, like to scale it up, right? Those are engineering problems. So therefore, I actually think to make quantum computing, quantum technology finally work, I think it's the right department to be in. That being said, though, that does not mean you should just stay in within your engineering bubble. Branch out, right? Because I really want to emphasize that it is multidisciplinary and we need to learn tools and methods from other fields.
Great. And then we'll transition into the senior design area. And then David is asking here if we have any quantum senior design projects at the moment that anybody is mentoring or doing.
The best of my knowledge, we don't have that many faculty yet who are experts in quantum. However, there is a research professor, his name is Professor Lukens. I think if you go to the Quantum Collaborative website at ASU, he offers capstone projects. I don't think they're at the size of a senior design project, but to get started, that would be something to look into. Or simply reaching out to me and we could probably figure something out. In general, also, I want to emphasize that if you have questions, please reach out to me. I'm happy to chat and explain a bit more what quantum is about and what it is not about, and offer guidance and opportunities. So, yeah.
Christian, this is James McDonald.
Oh, hey.
I'm the one that kicks you out of your room every at 3 o'clock.
Oh, I know. Hey, good to see you.
I just want to jump in. The question, I think I heard you say Professor Lukens. Is that right?
Yeah.
Yeah. No, there actually is. So whoever asked that question, there is actually a project in senior design called Quantum Link Compensation and Management, and Professor Lukens is running that particular project for senior design.
Yeah.
So.
Oh, that's wonderful. Thanks for asking that, David. That was a perfect segue into capstone discussion. So thanks, David. That was a great question. Professor Arens, thanks again for the presentation today and being our fearless leader of this exciting new area.
You're very welcome. Now, yeah, I'm excited about it too, and I'm particularly excited to work with different people from different fields, because I feel like that is the best you can do, right? That's bringing people together with different expertise to make this dream work.
Great, thanks. I think now that we know Professor McDonald is here, we're going to transition into the second half of our capstone presentation, which is about the senior design experience, the EEE 488 and 489 sequence. So thanks again, students, we'll do a quick transition here, and I'll introduce Professor McDonald, who's been with us about a year and a half or so, and he's a leader of our capstone experience for for one of the two sequences, either if you're starting in fall or spring. He's has extensive industry experience and entrepreneurship experience, and we're really grateful to have him on the ECEE teaching team. So thanks for being here, Professor McDonald, and you can start whenever you're ready.
Okay, can you all see that opening slide?
Yep, looks good.
Okay, and thank you for the introduction. So let's get moving here. So I'm going to talk to you, as Mr. Monahan said, about EE 488, 489, Senior Design Lab 1 and Senior Design Lab 2. These courses are essential to our program. They're kind of the culminating experience for our undergraduate electrical engineers. And one thing I want to point out in this presentation is how different they are from most of your EE courses. So let's just look at that in terms of what your current courses are. You're usually studying a set of fundamental engineering principles, whatever that might be. If you're taking circuits, from me, you'll learn about Ohm's law and Kirchhoff's current law, and you apply these principles to some basic kind of closed-end problems. And of course, you'll take quizzes and tests to make sure that you've learned and mastered those principles. And there's usually just one instructor. In my circuits class, there's just me. So that's the way most of your classes follow in your curriculum. No, in 488, 489, it's quite a bit different. What we're really trying to do here is take those principles that you've learned in those classes that form your foundation of your education and bring them together and apply those principles to open-ended projects, okay? And you're gonna learn also about soft engineering and things like manufacturability. You're gonna learn other things I consider soft engineering is how to communicate and work in teams. So that's something that is quite different. The project will be open-ended, meaning you're not gonna work on like a homework problem where it's like 8 plus X equals 10, solve for X, okay? It's more like, okay, we wanna work on something that impacts climate change, that mitigates climate change, and then what might we wanna work at and what work on and what different things are involved there and what would we want to address. And it's a very open-ended type of a project. There's no one set way to tackle it, if you will. And again, you are working in teams, and I'll talk more about that. The other thing is there's really two people involved in the EE program, the 488, 489. There is your technical mentor, which I'll talk more about. And they're kind of providing guidance and keeping you on the rails and helping you as you move forward on your project, offering perhaps some technical expertise. And then there's myself, who is referred to as the course coordinator. So there's kind of two people that you're working with and kind of, you know, responsible to, if you will. You're going to write, as I mentioned, reports. You're going to make oral presentations. You're even going to make videos, for example. And some of you, that might be the first time you actually even make a video presentation. So you're going to be working a lot on your communication skills, both written and oral. So this is a 2-semester course. The first part of it is 488. The second part is 489. And as Mr. Monahan mentioned, I teach the fall spring sequence, and Dr. Harton at this point teaches the spring fall sequence. Okay. Now, this is really, really an important point for all of you out there. You have to enroll in 488, 489 consecutively. Okay. The reason is you're going to form teams in 488, and you're going to continue working with that team on that project in 489. So as you can see, you can't take that semester off. So if you enroll in 488 in the fall, with me, for instance, you're going to take 489 in the spring, and you're going to have me as the course coordinator, and you're going to work with that same project team. All right. If you don't do that, then you're going to have to start over and do 488 again. All right. So please be aware of that. That's very important. Okay, so let's look at what we do in 488. Well, the first thing we do is we form teams. And I'll talk about that again later, but it's I like to call it controlled chaos. Projects and mentors are selected, all right? And then this is where you do kind of the customer discovery, the planning, the research, the design phase of the project. We added a proof of concept in this phase, which is where you identify the highest risk to your project and you develop something that mitigates the risk of that high risk portion, that you prove to yourself that, yes, this is going to work, because we don't want you to get all the way through 488 and find out in 489 that you have a concept that simply doesn't work, right? So that's why this proof of concept is very important. And this is done in industry as well. The lectures are twice a week for 50 minutes, and I try to include a lot of guest lecturers. The guest lecturers are either relevant to teaching you something directly for this class, which also will be important in industry. For instance, I might bring in a world-renowned person on project management and talk about project management. I'll also bring in industry speakers that talk about a particular industry. For instance, today we actually had the general manager of Moog in Gilbert come in and talk about what they do at Moog worldwide as well as locally, and the job opportunities and internships that are available. So we do bring in guest lecturers. Now in 489, this is when you execute. This is when you're really building out what you've planned out and kind of designed. You're evaluating it, testing it, and looking for opportunities of, okay, if I were doing a next generation of this, what could I improve? Okay. You document it in a final report. That's kind of a pretty big deal. And really how this all culminates is in a showcase and demonstration day. And that's a big day usually held on the last day of classes on a Friday. It may change, but for now, that's when it's traditionally been. And you demonstrate kind of what you worked on and what your project tackled. And it's open to the public. We'll get alumni that show up. Your mentors will often show up. Heck, I even bring my wife. So, it's really a pretty big deal. And it's a great way to literally showcase what you've done. And one of the differences in 489 is we only have one lecture a week, typically on the Friday, but it's for an hour and 15 minutes. And again, I continue to bring in guest lecturers. Okay, I'm going to kind of get into the heart and soul of the components for Senior Design Lab 1 and 2. And this applies to both. There's resources that you need for your project, the team that you'll be on that carries out the project, and then of course your mentor who's providing that guidance that I talked about. So let's look at the student team first and what you're going to be expected, how you're going to form your team and what's expected there. So teams must consist of 3, 4, or 5 members, no less and no more. Students form their own teams by connecting with each other. So this particular class consists of both an on-campus and online, and we combine that for this 488, 489. So you can be a completely on campus, completely online, or a combination of both. We're actually trying to facilitate what I'll call these hybrid teams so that you learn to work with people remotely, because guess what nowadays? That is what happens in industry. You have teams that are geographically dispersed. You might be working with someone in Pennsylvania, California, and you're in Arizona, or even someone on the other side of the world, okay? That's very common in the industry I come from, which is semiconductors. So we actually encourage hybrid teams. You can use Slack to facilitate. We'll set up a Slack channel that you can facilitate trying to form your team. And, as I mentioned, I do call it controlled chaos. There's approximately 240 students in the fall and spring. The fall spring, I believe, and correct me if I'm wrong, is typically the bigger class size. So we have 240 students, roughly 130 or 40 on campus and the other 100 or so online. So trying to keep both flexibility by allowing you to form your own teams and find projects that you're interested in means that it's not as structured. Clearly, we could just assign projects to teams and assign team members to the group, but that would be very inflexible, although there would be less chaos associated with it. So I like to call it controlled chaos, which we help facilitate the finding of teams and projects. And we basically provide almost a month for you to get together and find a team, find a mentor, and find a project. So don't stress about that. I guess that's the one thing, because I know this can be a stressful time in the beginning of the school semester. And again, as I mentioned, you're going to stay with that team through both 488 and 489. So it's a 2-semester sequence, and you'll be with that same team. So how do we look at this in terms of team versus individual work? Well, the coursework is going to comprise both, but a vast majority of the work you'll be graded as a team, okay? So there will be, like when you're presenting, for instance, 80% of that might be the team grade, and 20% is on how you individually presented your particular material. And then at the end of the semester, we will do an intra-team evaluation. And this kind of enforces accountability so that you don't have individuals that just kind of sit back and let everyone else do the work. And it also lets your teammates point out if you excelled and you led the team and took on a lot of additional responsibility. And again, I'm from industry, and this is very common in industry. They call it like a 360 feedback, where you evaluate the people you worked on a particular project. And this way, it's not just coming from your supervisor, but coming from your teammates as well. And again, this is not something that is going to take someone who has an A and take them to a C or anything like that. It's just a little bit of a weighting factor if you're kind of, on the border there between two grades. Okay, let's talk about a mentor. What is a mentor and what's their responsibility, and how do you work with them? So each team is going to be mentored by a professional, usually an EE faculty member, but sometimes it's from industry. Last year, we had a lot of industry projects. This we have a little bit less industry projects, but we still have a handful. Most of the time when we have an industry mentor, they come to us with a project. And we'll post these on Canvas. So if you like one of those projects, you can talk to the potential mentor and find out and perhaps form a team around that project. And there's already a defined project with a mentor, and then you have your team of 3 to 5. Some project mentors, typically faculty, will come to us with their own ideas, but other faculty mentors will say, hey, you know what, I want to mentor a couple teams, but I want them to come to me with their projects, because I find that if they define the project, basically there's more engagement and more interest since it's their project. They defined it. But in either case, the mentor is going to supply a big chunk of your course grade. In fact, the mentor is going to supply roughly 50% of your grade. And the mentor can choose to grade the team all the same or to give individual grades to each member of that team. Each group is required to find their own mentor. So if you're going to come up with your own project, then you can either look on Canvas and see if there's a mentor available that has that interest in that area, or you can go talk to other professors that you've had throughout your first few years and see if they're willing to be your mentor. And then one of the things I recommend is you can go to this link and you can look at what faculty has interest in, what their research interest is. So if you have something in solar and power, you can look at the team of faculty that has a particular interest in that particular area. And you might even want to do that as a precursor to starting this class. And again, I will list a bunch of projects on Canvas that are available. I will list mentors that will take projects from students, and then I will list mentors that already have defined projects and are willing and want to mentor those projects. So there's lots of options there. And again, most industry-based mentors will come from Canvas listing. Okay, so even though the mentor is responsible for 50% of your grade, they're not your boss, okay? And the reason I say that is this is a situation where you're in charge of your project and you are responsible for the success of that project. They're providing guidelines, they're providing perhaps some technical expertise, but you and your team, you're driving that project, okay? They're there to support and to help you. Again, they provide the support, encouragement, advice. Ideally, your mentor should be able to help you with technical aspects of your project and supply some resources. If they can't, hopefully they can point you in the right direction. They can point you to subject matter experts or certain resources on the web. Your project mentor should be good at breaking down your project into logical steps and achieving milestones. And that's really important in the beginning where you're going to set out your project plan, okay? And map out kind of the steps and the timeline for your project. Okay, let's talk a little bit about the project, types of projects and what a project is. Okay, so again, projects can originally, their origin of the projects can come from students. Okay, you can define your own project, come from faculty and research staff, and can come from industry partners. So there's a lot of opportunity of where you can find a project. And again, regardless of the origin, students own the project. Okay, they have full ownership and responsible for the success or the failure. And if I can recommend anything, and I always say this in the beginning, find a project that interests you. You don't want to be spending, roughly 6 months, 2 semesters, 7 months, working on something that you have literally no interest in. So find a project that you're interested in. Okay, let's just look at this quickly here. Project needs to be comprehensive and integrate multiple areas covered in your EE work. Okay, so this isn't just one particular area. It can have programming, it can have power, electromagnetics, RF, circuit design. Lots of different areas can be encompassed and required to successfully complete your project. Should be open-ended, challenging, and meet a societal need or want. We'll do customer discovery, where you'll start looking at, okay, what problem do my customers have and how can I help them solve that? And everyone has a different customer, if you will. But it's very comprehensive in what you need to bring. And the other thing I'll mention is, and I don't think I said it here, but you're going to learn some things too. There's going to be areas of your project that you're going to dig into that you really hadn't had a lot of exposure in your undergrad. And that's okay. That's a good thing. The other thing you have to keep in mind, and we talk about this as being scope of the project. And what that means is, what can you accomplish with a group of 3 to 5 senior engineers or senior undergraduate students in a 2-semester time frame with the constrainment of resources, be that money or whatever else. Okay, so you have to make sure your scope is compatible with these constraints, if you will. Okay, and then let's talk about resources, because that is some of the constraint. You should design things from the ground up with off-the-shelf components or subsystems. You can get access to components, development kits for little or no cost through the School of Manufacturers. We have some projects. We have a couple projects that are drone-based projects. I think one is real interesting, is to use a drone to clean rooftop solar panels, right? Because it's dangerous getting up on the roof. It's hot in the summer in Arizona. So can we get drones to do that? Well, we saved the drones from a year ago, so we already have 2 drones. So drones are expensive. You don't have to worry about that. If you raise your hand and you're one of the first 2 teams, you can get that drone, and therefore you don't have to worry about funding, getting funding access for that drone. So you try to make use and to get what you need at the lowest cost, and still be successful. And by the way, that's something required in industry as well. ASU provides a lot of free software for your design, and also just to manage the project. For instance, students have access to Microsoft Project. You can jump on that right away in the beginning to help plan out your project and your resources and what's called your bill of materials, etc. So take advantage of that. We have 3D printers available and access to machine shops at very discounted prices. And I'll actually list on Canvas a whole sheet of resources with contact information. So you'll be able to get access to that and follow up in those areas and find out if they have what you need for your project. Now, project budgets are pretty small in my mind, if you don't mind me saying. Roughly $100, $150 per team. But again, there is access to a lot of these things at discounted prices. And also, a lot of times, particularly in industry, They have a budget that they set aside for projects as well. And then there is one last option. In addition to faculty and industry, there is formally you can apply for some additional funding. They are limited, but you have to go through kind of a justification. It's a little bit more involved, but we can review that. Finance can review that, and we can potentially approve that to get you more funding. So there is some opportunity there to get more than that 100 to 150 per team. So senior design is going to help you develop soft skills required by employers. I believe this was from a survey. I don't remember the name, but they asked employers, what are the most important things you look for in terms of the skills by potential employees? And number one on the list is communication. And it's the most important skill looked for in interviews. All right. And I know in this class, a lot of students will say, I have to write too many reports. I have to do too many presentations, etc. But this is indeed listed as number one in terms of soft skills required. Problem solving abilities, breaking down complex problems into simpler parts. You know, I always relate to this I do marathons, and someone will often say, how do you run 26.2 miles? And I say, I never run 26.2 miles. I run 1 mile 26 times, right? I break it down into smaller, simpler, achievable. And then I end up getting to the end. So problem solving is another one. Working in teams, in interdisciplinary environments. You know, that's very important. Almost every project I've worked on in industry, we're working with mechanical or thermal or just different teams within EE, technical test engineers, product engineers, quality engineers. So learning to work in teams and be successful, very, very important. Working at and with project teams at multiple sites. And that goes back to what I said earlier, especially post-COVID, a lot of people are working remotely. They're working across the country, across the world. So learning to do that's very, very important. And then lastly, be aware of the business context. A lot of people, especially new graduates, they're so focused on the technical stuff that they don't realize. In the company I used to own, we had these 3 stools of the leg, and all stools had to be taken care of. And it not only was it the technical specifications, but it was the budget, so the cost, and then also the schedule. And you had to manage all 3 and be aware of all 3, because if any one of those, if you don't pay attention to it and it gets chopped off, well, you don't have a very stable stool to sit on. So be aware that there's other aspects, not just meeting a technical spec. And that's also very important. So there's a lot of course and student outcomes. This is an accredited class. I don't want to go through all of these, but I'll rush through them quickly, but they'll be on the syllabus as well. But being able to solve problems, design solutions that include things that you might not talk about in your other classes: public health, safety, welfare, culture, social, environmental, economic factors. Communicating effectively to all different types of audiences. When you're in industry, you have to communicate technically with all your peers, but also you have to communicate with management or perhaps non-technical people in finance or some other department. So learning to do that effectively is important. Responsibilities, ethical decisions, and again, focusing on environmental, society, the impact that it has globally, economically. Effectively working on a team. I can't tell you how important that is. That's probably one of the #1 things we looked for when hiring people at my former company was, can they work well in these teams and within the culture of our company? Experiment, analyze, interpret data, using engineering judgment to draw conclusions, and acquiring new knowledge. Again, you may not know everything you need to know to successfully complete your project. Being able to acquire that new knowledge and apply it is very important. So these are all emphasized as part of the capstone design. It brings technical and soft skills together, and really this is to prepare you for a professional career. And as I said, I spent 30 some years in the industry, so this is very near and dear to my heart. Remember, you're all entrepreneurs, all engineers are entrepreneurs. Have that entrepreneurial mindset. It's part of this capstone experience. Talk about the 3 C's. Be curious, constant change, okay? There's a book called Who Moved My Cheese? Read it if you haven't read it. It's a very simple read. You can read it in probably an hour or less. That's one thing constant is change, okay? Connections among information from many different sources. And I'll also say connections from people as well, okay, your network. And then making sure you're creating value. Creating value is where opportunity arises. Being able to solve a problem, look at what your customer, where they're struggling, and finding solutions, okay? We always want to create something that solves a problem. Sometimes people just want to create something really cool, and it's like, yeah, but how does it help me? Okay, we want to be able to create value, all right? In industry, obviously, when you create something, you want to be able to sell it. You want customers to pay money for it. So it has to add value. That's about it. That's a quick presentation. Senior Design Showcase tentatively on April 26th. If that changes, I'm sure there'll be announcements. I would suggest stop by, see what it's like, see what that culminating demonstration day is all about. I think it would be cool to see that and see where you're going to end up being a year later or 3 months, 4 months later. And you know, I'm one of 2 course coordinators along with Dr. Harton. So there's certainly a chance that I will see you in my senior design class, and I wish you the best of luck. And that's it for me.
Thank you, Professor McDonald, for the great presentation. I echo your request that anybody here show up to the capstone event, if possible, to interact with your students and see what the projects look like at the presentation. We do have a couple of real brief questions. If you have a second to hang on, we're almost out of time.
Sure.
But our capstone first, Zachariah, it's we do these are EE students working together. So there have been some historical examples of multidisciplinary teams, but those are difficult, and most other schools are not participating in multidisciplinary teams at the time. But if you have any, you can ask questions offline to your capstone instructor when you start. James is asking, yeah, go ahead, sorry.
We do have some projects that are with some startups, and the projects are within our EE are just the EE program, but they're linked to other disciplines that are tied in. And so the mentor is kind of, filling in that communication link between the EEs and the mechanical and the chemical, et cetera, et cetera. For instance, if you were designing some kind of electronic box, you might have to have information from the mechanical design team. That's a separate capstone, separate area, but you might have to have that information of how big can I make this, or what kind of power will I have available, things like that. So there is some multidisciplinary aspects, but the teams themselves are all, within EE, they're all electrical engineers.
Yeah, and then a couple of questions about the sequence. So correct, if you take it fall, spring versus spring, fall, there is a summer in the middle. Students are generally not required to do work during the summer, but some students do choose to continue their programs, working on their projects slowly through summer. Do you have any comments on benefits or challenges there, Professor McDonald?
Well, the first thing that I would say is, obviously I don't have that situation. So Dr. Harton would be a good person to talk to. I do have the situation where we do have a rather long break, roughly a month in most of December and maybe a first week of January. My rule there is, you know, everyone needs a break. There's holidays there. Don't plan on doing a lot of work. Really, that's for a couple reasons. One is because we've found over time that most of the time, not a lot of work gets done. And secondly, not all students on your team, you know, they may be traveling, you know, who knows, to India, or, you know, they may have some particular traditions, and they're not going to be able to work on it. And there can be this pressure of, yes, you have to work over the holiday break, you know, in December. And that usually creates more conflict than anything. So I don't think it's going to speed up your graduation if you work over the summer. I mean, it isn't. You still have to do that fall semester. So, you know, I think if you yourself personally want to dabble and do some things that you were working on as part of the project, that's great. But I would say probably there shouldn't be an expectation that someone's going to spend 2 or 3 months dedicated to working on their senior design. I think it's more likely that you should just figure on regrouping in the fall.
Yeah, that's correct. Some students, if that comes up, it's very important among the group to set some parameters so it doesn't cause problems. And then we will have our capstone in fall. Oh, what's the day? Cheryl, do you have the day in front of you? The demo day for fall semester?
For fall, we're going to have it December 1st. That's a Friday.
That's right, December 1st. More to come on that. We're going to probably be joining other schools and having a larger event. And we expect a Zoom option for online attendees. More to come on that. And we are out of time, so the rest of the questions, please ask your academic advisors if you can, or ask us again when you get to class, or you know, all of that stuff. But for the sake of time, I think we need to close it off. So thanks again for your questions and your attendance, students. Thanks everybody for being here, and special thanks to our faculty, Professor McDonald and Professor Ahrens, for speaking today.